Hello everyone. Yesterday we studied the sequences section, so today we'll continue to finish this section. So here's the note. Let's take a look at it. Example 5. Is the given sequence an equals n over square root 10 plus n convergent or divergent? Okay, so actually yesterday we did something similar. But our sequence, for the given sequence we did in the last class, we have the same power for the n for the denominator and the numerator. But here we have power 1 for the numerator and 1/2 power for the denominator, right? So when we have different power for numerator and denominator, what should we do? So we always divide by the highest power in denominator. Power in denominator. So the highest power in the denominator, for this case, we divide both by square root n. Divide by square root n. Okay, let's simplify this case. So we get numerator n over square root n, we get square root n, right? And denominator we get, so we put them denominator, the two square root into same square root. So it's going to be 10 over n plus 1 after we simplify. Now let's take a look at denominator. In the denominator, 10 over n goes to 0 when n goes to infinity. The limit is 0, right? So we can see, but for the top, we still have n left. So an goes infinity. In this case, our limit of an when n goes to infinity is infinity. So we say the sequence an diverges. O divergent. Okay. That's the example 5. Now let's take a look at a very similar problem. Exercise problem. So here we have this sequence. Okay, so can you tell this sequence convergent or divergent? You can take time to do your exercise. So it's good to pause my video and start to do the exercise and then come back to check with my answer. But now I'm going to give you the answer. So for this case, we divide both by n squared highest order power in denominator, right? And simplify. So it's going to be 1 over n, 3 over n squared, denominator 1 plus 5 over n plus 6 over n squared. And all those terms, they go to 0. So the final answer equals 0 over 1, which is 0. Right? So here I should write down the limit, okay, goes to 0. So in this case, this an converges. Did you get the idea of this kind of problem? There is also another way you can use. For example, in the example 5, for the problem an, numerator has higher power than denominator. Then n goes to, so when we use n divided by square root n kind of thing, so when n goes to infinity, this thing goes to infinity. So whenever we have higher power in numerator, it goes to infinity. But for this exercise problem, we have higher order power in denominator. So when denominator goes to infinity, faster, large, so that's why the limit goes to 0. So you can always tell by the order. You can also use that method to double check your answer. Okay. So next, let's go to our next topic, which is continuous function theorem for sequences. That is theorem 3. It's called continuous function theorem for sequences. So here we have a sequence an, and if an has limit, and limit is L, and if f is also a continuous function, then the conclusion is f an goes to fl. Okay, f an goes to fl. I'm going to show you how to use this theorem in an example, because it's hard to see from here, right? Example 6. Show that limit of this sequence is 1. Okay, let's take a look at this problem. Now we can look at the sequence listing as f(an). This is a function of an, and we can treat an as n plus 1 over n, and fx as, you can see, if this is f(an) and this thing is an, so what is fx? Fx actually is square root x, and this is continuous function, right? And an goes to what value? An goes to, from here we can say, we can easily see an goes to 1, and that is the L in our theorem, right? L equals 1. So what is fan goes to? Fan goes to fl. And what is fl? Fl is f1, because L is 1. And what is fx? Square root x. So square root of 1. The final answer is 1. Something like this. Okay. So for a given sequence, we find our an, find our fx. So the steps is find an and fx. Second step, find L, and what is L? That's the limit of an. And third step, find fl. Okay, we can always follow those steps. Now let's take a look at the exercise problem. An equals, let's see, 2n over square root 2n over n plus 1. Okay. let's say just to determine if this convergent or divergent. Let's see. For this sequence, convergent or divergent, and what's the limit? So same thing. Here we set up our an first step 2n over n plus 1, right? And here we can find L. Actually, what is L? L is number 2. Okay, and then we find our fx. Fx is same thing, square root x. And next step, fan goes to fl, which is square root l, which is square root 2. That's the answer, right? So before you do the exercise, please look at the steps in the example and then follow it. So for here, all my functions are like a square root. But if I give you a similar thing, for example, if I can give you this sequence, 2n over n plus 1 cube power for this sequence. So you know what is an, right? An is still this one. And what is fx now? X cubed now. So you follow the same step. Actually, this sequence, when you finish the calculation, this goes to 2 to the cube, which is 8. Okay, this is called the continuous theorem for sequence. To use L'Hopital's rule to find the limit of a given sequence. We know L'Hopital's rule is very powerful, so let's have a quick review what is L'Hopital's rule. Okay, so next topic, we want to use L'Hopital's rule. So we usually say LH, okay, rule. And what's the meaning of that one? So that means usually this is for infinity over infinity type, or 0 over 0 type limits. We do this way, okay. We can make the limit into f prime over g prime. That's the L'Hopital's rule. We learned this in Calc 2. Now, but L'Hopital's rule is for function. Here we have the sequence. Sequence has the variable like kind of like n. For example, if we have ln, n over n, this is our sequence. So the variable is kind of like an n, right? Before we use the L'Hopital's rule, let's do a theorem. By using the theorem, we can use L'Hopital's rule easily for sequence. So let's see. If limit x goes to infinity, fx equals L, and fn equals an, then limit n goes to infinity, an equals L. I will show you what's the meaning of this theorem. Actually, if we take a look at fn equals an, if we take a look at fn equals an equals, for example, ln over n. So we can ignore the middle term probably here. If fn equals this thing, you can see what is fx. Just ln x over x. So basically, we just change n in the sequence into x, because L'Hopital's rule works only for functions, not for sequence. But by using this theorem, we can change the sequence into function and then find the limit for the function, and that limit is just a limit for the sequence. That's the meaning. Now I'm going to show you in the example. Let's take a look at the same sequence, an equals ln over n. Okay, so if we want to find the limit of this an, we want to use L'Hopital's rule, but we cannot use L'Hopital's rule directly to this sequence. We need to use to a function. So firstly, we set up the function. Function is just ln x over x. Just change the n into x. This is our fx. And then we look at this function. We noticed it is infinity over infinity type when x goes to infinity. Right? So let's calculate this limit by using L'Hopital's rule. The L'Hopital's rule means we can take the derivative of the top function and the bottom function. Derivative of a denominator x is 1. Derivative of ln x is 1 over x. So actually, this is just x infinity goes to infinity, 1 over x. The limit is 0. And then we apply this back to sequence, and we say sequence has the same limit, it's also 0. Okay, now let's take a look at the next exercise. If we want to find the limit of this function, sequence ln n over ln 2n. Let's take a look. We want to use L'Hopital's rule. So first step, we say, what is fx? ln x over ln 2x. And then we find the limit for this function. ln x over ln 2x. And be careful here when we take the derivative. The top function is easy, it's just 1 over x, right? But the denominator derivative, it is 1 over 2x times 2. And here we use the chain rule. Chain rule, we learned this in Calc 1. That means the derivative of outside function times the derivative of inside function. So it's kind of like fx gx derivative, which is f prime times g prime. Derivative outside, the derivative inside. So here, derivative outside 1 over 2x, derivative inside 2. Right? And now let's simplify. After we simplify, 2 cancel out, and the limit x goes to infinity. 1 over x cancel out with 1 over x, so it's just 1. So the answer is just 1. And then we say the n goes to infinity, an has limit 1. Okay. Now let's take a look at some commonly used limits. Okay, so it's given by theorem 5. It's called commonly occurring limits. The first one, which is limit n goes to infinity, ln natural log n over n, which is 0. Actually, we did this in the example, in the previous example, right? Okay. The second one, n goes to infinity, nth root of the n, which is 1. Okay. Third one, n goes to infinity, x to the 1 over n equals 1 when x is greater than 0. This is always kind of means when n goes to infinity, you can see it's like a kind of x to 0. X to 0 is power 1, right? Number 4, limit x goes to infinity, x to the n equals 0. That is for x absolute value less equal to 1. Less equal. Let's take a look. What's the meaning of that one? That means, for example, 1/2 to the power n. We can change this into 1/2 to the n. So when n goes to infinity, it's kind of 1/infinity, so which is 0. Right? Kind of thing like this. When x is smaller than 1, we always has limit 0 here. Number 5. N goes to infinity, 1 plus x over n to the n is e to the x. Here for any x. Okay, for any x. Actually, when we define e, the number e, we learned this before, the e number is defined by 1 plus 1 over n to the n. This is a definition for the number e. So it's kind of like 1 to infinity number is e. And here we just add x there because this is e to the 1 power, right? This is more general, e to the x, and here is x over n. Something like that. Okay. The last one, limit n goes to infinity, x to the n over n factorial equals 0. Okay, that just means x in factorial goes to infinity faster to x to the n. So just a kind of like a who go to infinity faster. You can use them as formula. You don't need to memorize all those things. Commonly use the limits. You can use them in the quiz. Now let's take a look how to use them in example. Okay, how to use those formulas to find other limits. The first one, n goes to infinity, ln n squared over n. So firstly, we need to simplify this an. Here we need to use the power rule for natural log function or for all logarithmic function. So we can take the 2 to the front, ln n over n. This is called the power rule, right? If there's a power, we can move the power to the front. And then this equals 2 times limit n goes to infinity, ln n over n. And we know this is the first one, that is 0. So the final answer is 0. So here we use the first limit. Second one, limit of this thing, nth root of n squared. If we take a look at our commonly used limits, this has similar form as the number 2, but it is a little bit different, right? So we want to simplify also. Change the form. N to the square, if its power is on the top, if its root is at the bottom, something like that. And we change this into n to infinity, n to the 1 over n, and then square it. And n to the 1 over n is just same as nth root of n. So the limit is 1, so the answer should 1 squared, which is 1. Okay. Number 3. Nth root of 3n. Similar to number 2. Okay, let's take a look. Firstly, simplify 3n to the 1 over n power, and then distribute the 1 over n power to 3 and n separately, n to the 1 over n. Right? So now let's take a look at those two. For the first one, it's kind of like goes to which number? This one, we use the number 3. Commonly use the limit, number 3. The number is kind of like 3 to the 0, so which is 1. And the n to the 1 over n goes to also 1, so which is 1. Here. And then let's see the last one, number 4. Negative 1/2 to the n. This one goes to, by using number 4, when x absolute value less than 1. So here x is negative 1/2. The absolute value of negative 1/2 is 1/2, which is less than 1. So the limit goes to 0. Right. Let's try one more. Okay, one more. If we have an equals 1 plus 7 over n to the n, this goes to which limit? So let's take a look. This should go to e something, right? The formula, number 5 formula. Okay. X is 7, so this goes to e to the 7. We can write down the answer directly. Now let's take a look at some exercises problem. The first one, I'm going to give you this. Okay. Second one, third, in homework, you will also see similar problems. Okay, so here we have 3 problems. You can try them by yourself, and then check with my answer. The first one goes to the limit. Okay, I'm going to simplify 8 to the 1 over n. And this is kind of 8 to the 0 power, so final answer is 1. The second one is different from our formula, right? But we can change this into, in our formula is always 1 plus x over n. So can we change this into negative 1 over n? And what is our x then? Negative 1. Final answer is e to the negative 1, right? And the last one, 10n to the 1 over n, distribute the 1 over n, n to the 1 over n. So final answer is 1 times 1, which is 1. Did you get those 3 correctly? Okay, so that's everything we need to know in this section for the sequence. So for sequence, given sequence, we need to know several things. Okay, we need to know, we can say summary here. Summary. For the sequence, we need to know how to write out terms for a given sequence. For given formula an. Okay, an. For example, negative 1 to the n times 1/2. Oh, 1 over 2 to the n, something like that. And then write backward. So given sequence, how to find formula an. And second, tell a given sequence converges or diverges. That just depends on the limit of the sequence an, right? If the limit exists, converges. Limit that not exist, diverges. If it converges, how to calculate the limit of an? Calculation of limit of an. And here we can use several row method. We have commonly use the limit. We have L'Hopital's rule, right? We have continuous rule, function rule. So you can use all those kind of method. I think basically we just need to know those three things. Okay, we can stop here today for this section.